Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Reflections on the Parallel Mathematical Thinking. Edited by Jesus Velasquez Bermudez. HI enthusiastically celebrated that John Hopfield and Geoffrey Hinton have won the 2024 Nobel Prize in Physics for fundamental discoveries and inventions that enable machine learning with artificial neural networks. This recognition is a stimulus and a voice of encouragement for all scientists working in artificial intelligence. Mathematical revolutions. From arithmetic to parallel mathematical thinking. There is no doubt that the evolution of human intelligence is directly linked to the evolution of mathematics. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. However, for a long time, mathematics oriented to parallel optimization has been undervalued. In many of the academic programs they are totally ignored, and many of the students do not feel the need to use them. This lecture is an overview of what parallelism and optimization entails. As early as 1972, in the book Human Problem Solving, Newell and Herbert Simon stated, "There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied." Newell and Simon, 50 years ago, were clear about the supremacy of machines. Scientists should not be surprised by the world in which we have lived for a long time. Mathematical revolutions. From arithmetic to parallel mathematical thinking. There is no doubt that the evolution of human intelligence is directly linked to the evolution of mathematics. Two different worlds. Without fear of being wrong, it can be said that as people and organizations travel the path from arithmetic to parallel thinking, an abyss is being generated, which is concretized in the speed with which a society produces knowledge and wealth. For example, growing scientifically without handling algebra is a utopia. The difference created by the mastery of algebra with respect to arithmetic is an abyss, not a gap. The difference created by the mastery of computer algorithms with respect to manual problem solving or mental models is another abyss. Algorithms were devised long before the digital computer, but it is their implementation that breaks the speed barrier to solve problems, giving rise to a new era. Those who do not learn to implement algorithms will live in a world unknown to those who do. These people will have difficulty understanding the word algorithm and trying to imagine its meaning. The most complicated thing will be that they will have serious limitations to say what they want in this new era. We should be concerned about the mathematical life of engineers. Normally gifted and with a high IQ, they are proficient in algebra at the start of university and are expected to be prepared to reach the pinnacle of applied mathematical knowledge. But this knowledge stagnates throughout professional life, reaching its lower limit in Excel, which in practice is the abacus of modern times. Digital natives are the first children with a lower IQ than their parents. This originates in the scientific gap that is forming. Computer technologies. In less than 20 years since its creation, the world of sequential algorithms in digital computers began to disappear. 80 years later it still exists, but that is due to the abyss that has been created in society, including the scientific world. Although computer technologies are evolving rapidly, thanks to the world of Industry 4.0, mathematical programming has not, so there is no difference between what is taught before and after the Industrial Revolution. Again, mastering a new methodology creates one chasm, not a gap. This time the abyss can generate two different worlds in the scientific field, those who understand and live the parallelism and those who do not. The situation becomes more notorious when money begins to be essential to enter this new world. Within 20 years of its creation, the world of sequential algorithms and digital computers began to die. 80 years later it still exists, but that is due to the abyss that has been created in society, including the scientific world. Although computer technologies are evolving rapidly, thanks to the world of Industry 4.0, mathematical programming has not, and that is why there is no difference between what is taught before and after the Industrial Revolution. People continue to think of isolated, monolithic problems that are coordinated and cannot be integrated. However, the concepts of multi-problem models, which represent increasingly large and precise systems, are not the generalized evolution of mathematical programming. But the biggest problem is the fallacy that formal mathematical models are not necessary for humanity, and that it is possible to build a scientific world without a formal mathematical model, which scientists of the past did not attempt. Instead of talking about the death of methodologies due to their obsolescence, the future seems to be the continuous evolution of artificial intelligence and what it contains. A world in constant evolution, where methodologies live very fast and each new moment seems to be born, which opens new opportunities for humanity. Human brains, a swarm of neurons. The future. Artificial brains, a swarm of algorithms of mathematical programming. In 1962, the Dutch mathematician Jacques Benders published his theory of partitioning, which is a transcendental, not the first, step in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. The author believes that Benders never perceived that the true importance of his research lay in the fact that he had established the way in which two algorithms would communicate with each other, and they could become a universal language for communicating a swarm of algorithms. If large-scale multi-level optimization methodologies, based on the partitioning and decomposition of systems, are applied to obtain the smallest atom of a dynamic stochastic model, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms, working autonomously and permanently, to achieve the goal proposed by the decision maker. This algorithmic swarm approach is currently used, in artificial intelligence, to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level dispersion matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining results as a team. This algorithmic swarm approach is currently used, in artificial intelligence, to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level dispersion matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining results as a team. Joseph Louis Lagrange was an Italian mathematician and astronomer, whose main idea is Lagrange multipliers, a strategy to find the local maxima and minima of a function subject to equality constraints, using the implicit function theorem. Lagrange's seminal idea is to convert a constrained problem into such a form that the theory of an unconstrained problem can still be applied. The principles of Lagrange theorists are still the support of optimization, but solving real problems using their techniques is no longer valid. Without knowing it, Lagrange generated the foundations of communication between cognitive robots, which speak mathematics as their natural language, allowing them to move like an artificial hypothalamus. Power of computing and mathematical programming. The current state of computing technologies implies the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models, which can be executed in parallel. This allows us to talk about autonomous distributed optimization in real time. Mental intelligence supports the mental models that every human being needs to start making their decisions. Human intelligence has evolved along with human beings. To understand this process, High describes human intelligence as composed of three intelligences: mental intelligence, mathematical intelligence, and creative intelligence. High focuses on artificial intelligence for decision-making, which corresponds to mathematical intelligence. Human knowledge, mental intelligence. Mental model, It is the abstraction or conception of what individuals perceive about a certain topic or problem. Mental models are built with the individual's knowledge, experiences, assumptions, perceptions, intuitions, informal inductions, deductions, and values. They are elementary models that are not exposed in public and, therefore, have a validity limited to the individual. They have their origin in the evolution of the human being, hominization, from the most primitive ancestors, Australopithecus, to the appearance of our species as we know it today, Homo sapiens. All human beings handle mental models, very quick to solve, and, in their absence, they are easily copied from a more influential individual and, more recently, implanted in humans through the ochlocracy of mental models distributed by social networks. When intelligence works under this model, we will call it mental intelligence, which exists and develops in all human beings. The mental model is oriented to identify patterns, its foundations are not mathematical and respond to data processing and the evaluation of eventual and systematic experiences. It is based on good practices. Pattern recognition is a method of data analysis that uses artificial intelligence algorithms to automatically recognize patterns and regularities in data. This data can be anything from text and images to sounds or other definable qualities. Pattern recognition systems can recognize familiar patterns quickly and accurately. Pattern recognition is the activity that humans perform the most. For example, it identifies images of people, foods, hydroclimatic conditions, traffic conditions, texts, sounds, etc. All this with the aim of establishing the conditions of the environment, in the past, present and future, and based on this knowledge to make decisions. It's not known how the brain identifies patterns, but traditional artificial intelligence mimics it. Then, the starting point of the name artificial intelligence is associated with pattern recognition. Today, the association is direct, and it seems that artificial intelligence is reduced to this function of the human brain, which has concentrated much of the scientific research on working in this direction, forgetting other human brain functions. It seems that artificial intelligence is reduced to the emulation of mental intelligence, whose function is little known and explained. That is why scientists know that neural networks can predict how a system will behave, but that in general the parameters found cannot be explained, they do not have a clear content, just as humans cannot explain how this function works in the human brain. But it cannot be said that this approach was fruitless, since it effectively and massively replaces activities that ordinary humans did not believe machines could perform. Initially, neural networks aimed to find ways to connect artificial neurons, with the goal of improving prediction results. Something like a statistical model in which many algebraic models are tested, until a good solution is found. Little has evolved to try to explain the content in this connectivity. This is the case with GPT. Pattern recognition is a basic human skill. The essence of the so-called artificial intelligence is mental intelligence represented through the study of biological neurons, to emulate and surpass the recognition of human patterns. The way in which the brain identifies patterns is not known, but it is successfully imitated by traditional artificial intelligence, which does so at speeds incomparable to the slowness of human beings. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the article, A Logical Calculation of the Ideas Immanent in Nervous Activity. McCulloch and Pitts attempted to explain how the brain could produce highly complex patterns, by using many basic cells that are connected. Neural networks were growing, and in practice they took the name of artificial intelligence. They were also called machine learning. Related aspects are mental intelligence, biological neurons, artificial neural nets, and generative pre-trained transformer. GPT is the state-of-the-art of the standard artificial intelligence. Mathematical intelligence underpins the mathematical models that some humans develop to make their decisions. Mathematical model is a scientific representation in any science, which uses mathematical language to describe the reality that is of particular interest to an individual. It is the result of research carried out by certain scientists. Understanding it requires formal training in mathematics and in the science being modeled. These models increase the intelligence of human beings, creating great differences, chasms, between them. When intelligence works under this model, we will call it mathematical intelligence. This ability to understand and handle mathematics does not extend to all human beings. It is necessary to acquire knowledge and experience to properly handle this information. Currently, its development is directly related to the ability to handle computational and mathematical technologies. Mathematical models are growing as analytical tools that provide greater processing speed to research. Since the creation of AI, it can be said that predictive methodologies, such as neural networks, displaced prescriptive ones, optimization, in what was called artificial intelligence. For the author, the only explainable reason is the comfort of the human being, and the search for commercial success. Artificial intelligence for decision-making is based on the development of mathematical intelligence, which focuses on the representation of the physical world through algebraic formulas and solves problems using exact mathematical algorithms. The displaced methodology is formal mathematical modeling, using algebraic equations and/or differential equations. This is related to the use of mathematical programming, or optimization, to support decision-making. It is easy to show that in most companies mathematical programming is not considered necessary, since the knowledge and the economic benefit it produces are unknown. That's because decision-making doesn't worry researchers promoting artificial intelligence much. Practitioners, perhaps fanatics, of traditional AI have classified mathematical programming algorithms as the exact methods, not with the intention of highlighting them or promoting their learning. On the contrary, they disqualify them because, in theory, they cannot be used. But this is false. The problem arises in the ignorance of non-scientists regarding the use of these tools, and in thinking that traditional artificial intelligence, such as GPT, solves all problems. The result of mathematical modeling of intelligence, based on neuroscientific studies to produce artificial brains. Artificial brains. There is only one chance to win: who can create knowledge? That's the question. The creator of the human brain conceived it as the integration of three main organs or systems: the neocortex, the hypothalamus, and the hippocampus. The hypothalamus is part of the thalamus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. Artificial brains correspond to the scientific foundations, more specifically to the mathematical foundations, which allow multiple mathematical models, algorithms or robots, to be connected, exchanging information between them to obtain a common goal, and act as holistic intelligence of organizations, or parts of them. Like the human brain, the artificial brain is made up of the following artificial components: neocortex, hypothalamus, and hippocampus. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. Neuroscientific studies associate the network of neurons in the cerebral cortex in layers, and in columns, connected in an organized and hierarchical way. In mathematical models, it is common to use an array that relates columns to variables and equations to rows. Normally, these matrices are scarce. Structurally like the human cortex. In mathematical models, it is common to use an array that relates columns to variables and equations to rows. Normally, these matrices are scattered. More information at: Why does the neocortex have layers and columns? A theory of learning the 3D structure of the world. This section is based on the paper Why does the neocortex have layers and columns? A theory of learning the 3D structure of the world. Neocortical regions are Composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects that extend well beyond the receptive field of individual cells. The image presents the hierarchical distribution of neurons in the neocortex, joining brain, neocortical columns, simple neurons and ion channels. This is the starting point of the Hawkins model. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. This structure has the same characteristics as those generated when a monolithic model is divided and decomposed into an atomized model, to process it in parallel. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. Like the human hypothalamus, the artificial hypothalamus must coordinate all the processes carried out by the artificial brain, exchanging information between them to obtain a common goal, the well-being and stability of the organization. This activity should be based on processing. Autonomous, mathematical models can be run autonomously, when needed. Parallel, atomized models oriented to be solved following asynchronous methodologies, and distributed, multiple models running simultaneously, on multiple computers, representing multiple types of agents. When we talk about the artificial hypothalamus, we could say that God does not play with mathematics. The human hippocampus is the part of the brain that stores experience and knowledge gained over time. The learning process of the human being is materialized in memory, which accumulates information to face each new situation, using the knowledge accumulated up to the moment of an action. Artificial hippocampus. This information is stored in the hippocampus, where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last few days, begins to fail with age until it is lost, due to its intensive use. While long-term memory can store very clear data, but it requires a longer access time to locate, remember, it. The artificial hippocampus is an expert system that stores two types of knowledge. Formulation of the mathematical models already tested. This information remembers all the mathematical elements such as constraints, problems and models. Historical data of the results generated by solving the mathematical problems, using large-scale optimization methodologies. This information is used as a starting point in future uses of mathematical models to support decision-making. Creative intelligence is the fundamental basis for the development of mathematical theories that support mathematical models. For High, this is an area of knowledge that it does not yet know. We are currently walking the path of creative artificial intelligence. To evolve from mental intelligence to mathematical intelligence, the human being needs another type of intelligence that allows him to perform the analyses to discover and understand the mathematical models that govern the universe that, according to Galileo Galilei, are written in the language of mathematics. We will call this intelligence analytical creative intelligence. This intelligence can be considered the highest level of human intelligence, since it is what allows the discovery of mathematical laws and, in general, of new knowledge, which are the engine of human science and technology. In practice, very few humans have this ability and discipline. But the results of their work benefit all of humanity. While humans in prehistoric times did not have access to mathematical intelligence, because they were creating it, today it is the engine of human knowledge, and ideally should be handled by all humans. Unfortunately, this is not the case. Therefore, its management must be part of the artificial intelligence that humanity is creating. The same thing happens with creative intelligence, the knowledge created by scientists, and the way to produce it is part of today's human intelligence. Proof of the above is the speed with which we produce knowledge. It took many centuries, hundreds, to produce algebra, but mathematical knowledge every day occurs faster, and extends its borders. For example, since 1947, with the appearance of the digital computer, a new science has been created: mathematics for computers. First monoprocessors, today parallels. This must be part of the artificial intelligence of the future. When the previous trend changes, humanity will have begun its disappearance process. Artificial brains are artificial intelligence plus mathematical programming, and are the result of HI's research into disruptive mathematical modeling methodologies for Industry 4.0, serving as theoretical support for optimization systems throughout the enterprise. For more information, those interested are invited to watch the video. Artificial brains, integrating artificial intelligence and mathematical programming. The artificial brain is the evolution of decision support systems under the Industrial Revolution 4.0, which is conceptualized as a set of autonomous mathematical models that exchange information between them, working online, using distributed optimization. This is how the human brain faces reality, using multiple models of reality, each of them acting permanently, in parallel, to make decisions, when it is considered that the information is sufficient. Based on the models to be integrated, and considering the magnitude, and the association between them, it is considered that the hypothalamus of a refinery business should be made up of 5 subsystems: petroleum refining and petrochemicals, industrial refinery services, water treatment, multimodal transport, and financial and tax. Large-scale optimization and artificial brains. One of the fundamental ideas of the artificial brain is the atomization of the system, with a bottom-up approach, to integrate multiple atomized mathematical models, using the framework of large-scale optimization methodologies, such as multi-level Bender's theory and Lagrange relaxation. To visualize the difference between the information provided by the solution of a monolithic model and the coordinated solution of multiple atomized models, we can imagine a medical examination based on a photograph and another based on an X-ray. Photography does not allow us to understand what happens inside the human body, but X-rays do. The internal visualization of a system is an advantage that cannot be achieved with a monolithic vision, which only provides aggregate information. Atomization allows us to understand how the system is assembled and how information flows within it. As referenced by Jeff Hawkins in his book A1000 Brains, there are multiple dimensions from which an artificial business brain can be viewed. In this case, the spatial dimension applies, where there is a model for each industrial facility. When all the models that make up a company are solved using the concepts of autonomous real-time distributed optimization, an artificial hypothalamus is obtained. Autonomy implies that models can act independently, without the involvement of a human command, and in real time, which can happen at any time. The concept of distributed optimization is associated with models that represent different agents, and that working as a team, solve a common problem, running in parallel. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, and its marketing process. The current state involves the integration of edge computing and cloud computing to implement highly complex mathematical models. These models can be executed under the modality of autonomous optimization distributed in real time. The integrated model, the artificial brain, can be distributed among several computers. OptX is the proprietary tool used by HI to develop and deploy enterprise-level optimization (AWO) solutions, in which multiple mathematical models converge and can be connected via disk or cached databases to form a monolithic model of the company. OptX is the generative artificial intelligence produced by HI, which manufactures enterprise-level optimization systems, EWOS, for all types of industries. Created in 1991, OptX is now the only computing tool capable of integrating hundreds, if not thousands, of mathematical models, running on a parallel and distributed computing system. Those interested in learning more about OptX can check out the LinkedIn article. OptX, the exacortex for mathematical modeling. Programming using programmers. Building an EWOS for a large enterprise, integrating multiple large-scale models using a computer programmer, is an impossible task. This is because the programmer can only write a limited number of lines of good source code per period. If there is more than one programmer involved in the process, maintaining the models can be more complicated than making them. Programming with cognitive robots. Only a generative artificial intelligence can produce infinite lines of perfect source code in seconds. OptX GPT is the research and technological development project that is currently being carried out by HI, to replace obsolete input interfaces with intelligent interfaces based on GPT concepts.
La nueva forma de las matemáticas está directamente relacionada con el pensamiento paralelo. Hoy en día se puede decir que, al igual que las matemáticas en papel, las matemáticas secuenciales para ordenadores de un solo procesador serán a corto plazo una lengua muerta. Al igual que en el cerebro humano, en el futuro solo el pensamiento matemático paralelo será práctico. La nueva analítica es autónoma, paralela y distribuida.
Not teaching young professionals the principles of parallel reasoning, derived from the new mathematics, is a serious mistake. Each society that does so will end up paying its consequences, which in words will lead to poverty and a growing scientific backwardness, an abyss, which generates two different worlds, which will not be compatible. Albert Einstein said, "Imagination is more important than knowledge, because knowledge is limited, but imagination surrounds the world. Knowledge will get you from point A to point B, but imagination will take you everywhere." Thank you for your attention.